When we looked at deriving the Fourier series, we generated this dot product of two functions. So if you had a function f of x and g of x, then the dot product of these two functions was the integral from minus pi to pi of f of x times g of x by dx. Now, whenever we were working with simple vectors, then we could say that if we had a vector en hat and we did the dot product again with en hat, we would get a value of 1. Similarly, if we looked at en hat dotted with em hat, we'd have a value of 0. So remember, all this is just telling us is that we're going to have a vector in this direction here. Let's say we call it en hat. So it's going to be length 1. And we're saying how much of this en hat is in the direction of itself. And the answer to that is all of en hat is in the same direction as itself. So that would give us a value of 1. But if we had the example here where we had our en hat is in this direction and the em hat is in this direction, and we asked what factor of en hat is in the direction of the em hat, and in this instance here there's no part of en hat that goes in this direction. All of it goes in this direction here. So the answer to that would be a value of 0. So the en and em hats are providing our orthonormal basis. But now we've got not these simple orthonormal bases here. Our orthonormal basis is going to be given by the values of 1, cos nx and sin nx. So it means that we have to be able to show that this dot product here, it does actually provide us with an orthonormal vector space which has got the basis functions 1, cos nx and sin nx. So rather than showing this here and this here, what we have to show is for the orthonormal basis 1, cos nx and sin nx, we're going to have the 1 dotted with 1, so that's this equivalent of this here, and also the cos nx dotted with cos nx, and also the sin nx dotted with the sin nx. Those are all going to give us the value of 1. So we're going to have to show these three here, this one, and this one, and we have to see that they do give us a value of 1. Now equally, we're going to have to show the second option here, which is the equivalent of the en hat dotted with the em hat, which is this example here. But now again, we don't have the simple unit vectors, we have the functions. So we're going to have to show that the 1 dotted with the cos nx is equal to the 1 dotted with the sin nx, and we're also going to have to show that the cos nx with the cos mx is equal to the sin nx with the sin mx, and finally we're going to have to show that the mixed value, which is going to be our cos nx dotted with the sin mx, is going to give us the value of 0. So actually in between each of these it's the dot product, so that's a little dot in there, okay, and also the dot in there, and also the dot in there. So it's the dot product for each of these. So if we're able to show that this is the case for these three, and this is the case for the other 5 here, then we are able to show that this dot product does actually work for this particular set of orthonormal basis functions. So let's go ahead and we'll do these 8 different proofs over the next couple of pages. So I've taken a copy of what it is we're wanting to prove. We want to show that the 1.1 is equal to the sin nx sine dotted with sin nx, which is equal to the cos nx dotted with the cos nx, and that should give us a value of 1. So we start off with the first one here, 1.1. So 1 dotted with 1 is going to be the integral from minus pi to pi of 1 by dx. So when we integrate that, it's going to give us a value of x from pi to minus pi. So that's going to give us pi minus minus pi, which is equal to 2 pi. Now note that that doesn't give you the value of 1. So that's not what we're looking for. But that doesn't matter because it's just a constant factor and we can divide out by 2 pi at the end. Now the next one along is going to be the sin nx sin nx. So we can integrate that from minus pi to pi over sin nx by dx. And that's sin squared nx by dx. Now we can use the identity a half 1 minus cos 2nx by dx. Now whenever we go ahead and integrate this here, this is going to give us one term here. So that's going to give us the x upon 2 whenever we integrate it. Now this second part here, we don't actually need to go ahead and integrate this part because we know that whenever we integrate a cos, we're going to get a sine. Now the sine is going to be an odd function, which means that if we were to work out the area of the odd function from 2 points that are equidistant from the origin, then this area here is going to cancel with this area here and we'll get a value of 0. So we don't need to bother about this factor here. So we're going to be left with a half x from pi to minus pi. That's going to give us our pi upon 2 minus minus pi upon 2, which is a value of pi. Now again, this doesn't equal the value of 1 above, which is what we required, but it doesn't really matter because it's just a constant term. So to get the correct dot product, we can just divide throughout by this term of pi. Now finally, the cos nx, again it's going to be given by the cos squared nx, and we can use the identity cos squared nx as a half cos 2nx plus 1. Now the same thing occurs here whenever we do the integration of this term here. Again, the cos was going to give us the sine, and the sine is going to be an odd function. When we integrate the odd function from minus pi to pi, that will give us a value of 0. So the only term we're going to be left with is the value of a half. So when we integrate the half by dx, we're going to get a half x, and that's from pi to minus pi. And again, it's going to give us the value of pi, and it's not the value of 1 which we require. But again, we can just divide throughout by pi because it's a constant and we get the correct dot product. So it means that the dot product for the 1.1, which is our constant term, is going to be given by 1 upon 2 pi. So we've had to divide throughout by the 2 pi to get the correct dot product. So that's one of the dot products, 1 upon 2 pi. Now the other dot product for these two here is going to be just the 1 upon pi. And that's the integral from minus pi to pi of f of x times g of x by dx. So this is the only anomaly that we see whenever we try and work out our dot products. So our dot products are slightly different depending on whether it's the 1.1 or whether it's the sin nx, cos nx, cos nx. So let's go ahead and we'll look at the other 5. So this is the other 5 here, so we're going to have this on, so that's 1, 2, 3, 4, 5, and we want all of these to equal 0. So we'll take them one at a time. So we're going to have the 1 dot sin nx, so that's just going to be the integral from minus pi to pi of our sin nx by dx, and that gives us minus 1 upon n cos nx from pi to minus pi. We'll take out the minus 1 upon n, we're going to have our cos pi, minus cos of our minus pi, which is going to be minus 1 upon n. Well, cos of pi is going to be minus 1, and that's minus the value of minus 1. So this minus cancel gives a plus. That is minus 1 plus 1 gives us a value of 0. So that's correct. It gives us what we require. Now you can work through the exact same process for the cos nx, and I'll leave that. I won't bother talking. You can see it for yourself. Okay, you can always pause the video. And again, we get a value of 0. Now, the last three here, 6, 7 and 8, we're going to use, again, a trig identity. So we're going to have cos n times the cos m is going to give us, now the half angle formula is going to be a half of cos n plus m plus cos n minus m. And we're going to integrate that. Now, when we integrate that, it's quite straightforward. It's going to give us a value of 0. And you can see why that is if we take each of these individually. So we can take this term here and this term here. Well, the n plus m, we could just call that a different value. We could call that, say, cos L. This here is nothing other than what we've done up here. So we could replace the n with this n plus m, and we're going to end up with the value of 0. So we'll have a 0 for this term here, and we'll have a 0 for this term here. Now we could work through each of these individually, and this is the other trig identity for this one, and finally the trig identity here for this one. And in each case, each of the values is going to give us a value of 0. So we'll end up with a final value of 0, 0 and 0. So it means that for these values of our orthonormal basis, we don't have any problems. All of them end up being a value of 0. So we don't have to any problems there with the constant terms. So that is a proof that the dot product that we require is given by, if we go to the previous page, is going to be given by these terms here, 1 upon 2 pi, the integral from minus pi to pi f of x times g of x dx, and 1 upon pi, the integral from minus pi to pi f of x g of x by dx. So these are going to be the dot products that we can use, and with these dot products we know that the value for our orthonormal basis 1 cos nx and sin nx is correct. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.